Welcome, everyone. Today, we are bridging the gap between data science and cloud engineering. We will master how to deploy Azure Machine Learning workspaces using infrastructure as code specifically, utilizing Bicep and the Azure CLI. Let's elevate our deployment strategies from manual clicks to robust, automated code. Let's start with the fundamental concept, infrastructure as code, or IaC. Traditionally, deploying an Azure Machine Learning workspace meant logging into the portal, clicking through menus, and manually typing names. This approach does not scale. What if you need identical environments for development, staging, and production? IaC solves this by replacing manual steps with code. You define your ML infrastructure in a text file. Why is this mandatory for modern MLOps? Because code can be version controlled, reviewed by peers, and executed perfectly every single time. It guarantees consistency. When we use a declarative language, we don't write scripts detailing how to build the server. We simply state what we want. The Azure engine handles the provisioning intelligently and idempotently, ensuring the final state always matches your code. Look at the contrast in this flowchart. On the top path, manual portal clicks inevitably lead to human error and inconsistent environments. Imagine forgetting to enable a specific security flag in production. On the bottom path, using infrastructure as code ensures that your deployments are automated, version-controlled, and result in perfectly identical, reliable environments every single time. To implement our IaC, we use Bicep. Bicep is Microsoft's domain-specific language designed exclusively for deploying Azure resources. If you have ever looked at a traditional ARM template, you know it is essentially thousands of lines of highly complex JSON. JSON is a data format for machines, not a programming language for humans. Bicep fixes this. It provides a clean, concise, and easy-to-read syntax. Why do architects love Bicep? Because it provides deep integration with Azure, immediate type safety, and validation right inside your code editor. You catch errors before you ever deploy. The way it works under the hood is fascinating. Bicep is a transparent abstraction. You write the clean Bicep code, and at deployment time, it is seamlessly translated into the underlying JSON that the Azure Resource Manager requires. This diagram illustrates the Bicep compilation lifecycle. You, the engineer, work exclusively at the top level, writing clean Bicep code. When you trigger a deployment, the system automatically transpiles that Bicep file into an ARM JSON template. That JSON is sent to the Azure Resource Manager, which acts as the orchestrator, reaching into the cloud to provision your Azure Machine Learning workspace. Before we write our Bicep code, we must understand the architecture of an Azure Machine Learning workspace. A workspace is your centralized hub, but it does not run independently. It relies on a hub-and-spoke architecture consisting of 4 critical dependent resources. You must provision an Azure storage account to hold your datasets, an Azure Key Vault to securely manage connection strings and secrets, application insights to capture telemetry and monitoring data, and an Azure Container Registry to store the Docker images used for training environments. Why this modular design? Because it leverages Azure's specialized services for maximum security and scale. The brilliant part of Bicep is how it handles these dependencies. If you pass the ID of your Key Vault to your workspace, Bicep's engine automatically determines the deployment order. You don't have to map it out manually. Look at the core architecture mapped out here. At the top is our primary goal, the Azure ML workspace. But observe the arrows pointing downward. The workspace fundamentally requires the storage account for data, Key Vault for security, application insights for observability, and container registry for environments. In our Bicep code, we will provision the 4 bottom resources first, so the workspace has everything it needs to successfully instantiate. Let's break down the actual code structure. A Bicep file is built using 3 primary building blocks: parameters, variables, and resources. Parameters are inputs provided at deployment time, such as the environment name like dev or prod. Variables are internal configurations calculated within the script, such as dynamically generating a globally unique storage account name. Finally, we use the resource keyword to actually declare the Azure services. By using parameters, we ensure our Bicep file is highly reusable. We never hard-code environment-specific values. For the deep dive, consider security. When passing sensitive data, such as an authentication token or password, we apply the @secure decorator to the parameter. This guarantees that the secret is masked and never exposed in plain text within Azure's deployment logs. This flow represents our Bicep code logic. On the left, we accept parameters, highlighting secure secrets and environment names. These flow into our variables, which compute names and configurations. The variables then feed into the actual resource declarations. Notice the implicit link from Key Vault to the ML workspace. By referencing the Key Vault's output inside the workspace declaration, Bicep links them automatically without extra code. You have written a beautiful Bicep file, but it is just text on your machine. To bring it to life, we use the Azure Command Line Interface, or Azure CLI. The CLI is the bridge between your local environment and the Azure cloud. To push our code, we use a specific command, AZ deployment group create. We pass it our resource group, point it to our .bicep file, and feed it our parameters. The CLI authenticates, bundles the code, and instructs Azure to build our ML workspace. But here is an expert tip: never deploy blindly. Always use the what-if operation by appending that C flag to your command. What-if acts as a simulation. It queries Azure and returns a detailed, color-coded preview of exactly what will be created, what will be updated, and, crucially, what might be deleted. You review the simulation, confirm it is safe, and only then does the deployment proceed. Follow the sequence diagram to see the what-if workflow. The developer submits the deployment command with the confirmation flag to the Azure CLI. The CLI sends a what-if request to the Azure cloud. Azure calculates the impact and returns a preview of all resource changes. The CLI displays this to the developer. Only after the developer manually confirms the changes does the CLI trigger the actual, final deployment. As your machine learning projects grow, a single Bicep file becomes a massive, unmanageable monolith. To achieve enterprise scale, we use modules. Modularizing Bicep is exactly like creating functions in software engineering. Instead of writing everything in one place, we create a dedicated storage.bicep file, a keyvault.bicep file, and an mlworkspace.bicep file. Our main.bicep file simply orchestrates and calls these modules, passing parameters downward. Why do this? It adheres to the dry principle. Don't repeat yourself. It makes debugging incredibly easy. For the deep dive, consider a large enterprise with multiple data science teams. You can actually publish your perfectly crafted Bicep modules into a private Azure Container Registry. Now, instead of writing code from scratch, any team in the company can securely pull down your pre-approved, security-compliant ML workspace module and deploy it in seconds. This visualizes a highly modular architecture. At the top, the main.bicep file acts purely as an orchestrator. It contains no direct resource definitions. Instead, it invokes the storage module, the Key Vault module, and the ML workspace module, injecting the necessary parameters into each. These individual modules then execute against the Azure subscription, building out the comprehensive environment cleanly and efficiently. Executing CLI commands from your laptop is fine for testing, but it is not an enterprise standard. We must remove humans from the deployment process by integrating our Bicep and Azure CLI logic into CI/CD pipelines, such as GitHub Actions. How does this work? We write a workflow YAML file. When a developer pushes a change to the repository, GitHub automatically spins up a virtual machine, logs into Azure using a secure service principal, and runs our AZ deployment commands. Why is this critical? It ensures that every deployment is fully automated, auditable, and secure against manual tampering. For a deep dive, we implement environment gates. We can program the pipeline to instantly deploy the Bicep code to our staging environment for testing. However, before it touches the production environment, the pipeline halts and mandates explicit human approval, protecting our live machine learning workloads. This flowchart maps out a secure CI/CD deployment. It begins with a git push, which triggers the GitHub Actions runner. The runner securely authenticates via an Azure login node. It automatically deploys the staging Bicep code. Then, it hits the crucial manual approval gate. The process pauses completely until a manager verifies the staging health. Upon approval, the final step executes, deploying the Bicep code directly into the production environment. Let's apply all of this to a critical, real-time use case. Consider Prosware, a healthcare startup building a diabetes classification model. Initially, they built their workspaces manually. A developer forgot a setting, leading to a misconfigured production environment that risked exposing sensitive patient data. This is a nightmare scenario for healthcare compliance like HIPAA. To solve this, Prosware transitions to infrastructure as code. They write a single, modular Bicep codebase. Using GitHub Actions and the Azure CLI, they pass a parameter, either env equals dev or env equals prod. Here is where IaC shines. The Bicep code contains conditional logic. If the parameter is prod, the script automatically disables all public network access and provisions secure private endpoints for the Azure ML workspace. Using one codebase, Prosware guarantees that their dev environments are open for easy experimentation, while their prod environments are automatically locked down like a fortress. In our final diagram, we see the power of dynamic infrastructure as code at Prosware. A single bicep codebase acts as the source of truth. When GitHub Actions passes the dev parameter, it deploys a workspace with public access for the data scientists. However, when passing the prod parameter, the bicep conditional logic intercepts. It overrides default settings, deploying a production workspace secured strictly behind a private endpoint. Complete automated isolation.